Hello, dear students. My name is Anna Frolova. I am a scientist at the Lebedev Physical Institute of the Russian Academy of Sciences. I work in the Optics and Complex Quantum Systems Laboratory, and today I'm going to tell you about memristors. Consider current processors. They have a so-called von Neumann architecture, which means that the processing unit is separated from the memory unit, and operations require constant exchange of data between the two units. This exchange actually accounts for 90% of thermal energy losses, which makes von Neumann architecture energy inefficient. This is where memristors come in, as they allow memory and processing all in the same device, drastically reducing energy consumption, potentially by up to 3 orders of magnitude. Apart from energy efficiency, memristors also provide passive memory storage, hence the name memristor, which means resistor with memory. This term was introduced in the fundamental work by Professor Leon Chiua in 1971. Chiua's theoretical proposal of a memristor stemmed from the search of the fourth fundamental circuit element. The first three being, as you know, memristor, capacitor, and inductor. Nowadays, we don't consider memristor to be a fourth fundamental circuit element, but as Chiua predicted, these devices indeed possess memory effects. This memory effect is based on the fact that resistance of a memristor depends on the total charge that has passed through it beforehand, so effectively it remembers this charge. The theorized device remained mostly unnoticed until 2008, when Strukov and his colleagues at Hewlett-Packard Labs created the first experimental implementation of a memristor, and since then the interest in these devices has been on the rise. One of the most notable applications of memristors is the design of devices that mimic biological neural synapses and neural networks. In a sense, memristor can be treated as an analog of a neural synapse, because they can both be described with the same mathematical equations. Let's consider a simple memristor, one from the Strukov's work, which is just a titanium oxide film between two electrodes. When the applied voltage is zero, the whole film consists of titanium O2 molecules, and the resistance is very high, equal to R off. Once we apply some non-zero voltage V, some of the oxygen atoms leave titanium oxide, creating a zone of some thickness H, which becomes doped with oxygen ions. This doped zone now has some free charges, because having lost one oxygen atom, titanium oxide molecule has two unbound valence electrons. Hence, the resistance of the zone is significantly lower than R off. We'll call it R on. This allows us to write down Ohm's law. So voltage equals to current times resistance, and to calculate resistance, we need to account for doped and undoped zones. So we have R on times H over D plus R off times D minus H over D. The border of doped zone moves to the right when the voltage is increased, and it also can move to the left when we switch the polarity, as oxygen ions recombine back into titanium O2. So another equation we can write down is for the velocity u of this border, which is equal to the first derivative of h by time, and is equal to mobility of the ions mu times electric field strength E. We can rewrite this set of equations in a more general way. So for Ohm's law, we replace resistance with conductance, G, which is the inverse of resistance, and G now is a function of voltage V and some state parameter S. The second equation is for the state parameter, so the first derivative of S by time equals to some function F, a function of the state parameter and voltage. If the applied voltage is periodical with some frequency omega 0, by plotting voltage versus current for this set of equations, we obtain a hysteresis curve. This hysteresis curve pinches at the 0 point, because zero voltage means zero current. As you can see, this is a double-valued function, which means that for each value of voltage, we have two different values of current. And in fact, it is clear why it has to be so, because in absence of memory effects, there would be an ordinary single-valued function. Here, since the resistance depends on the history of the flow charge, for a given voltage we can have two different currents. At a very high voltage frequency, 10 omega 0, the hysteresis collapses into a straight line, which is a current voltage characteristic of a plane resistor. This happens because at such high frequency there isn't enough time for sufficient movement of oxygen ions to occur, which would have changed the resistance. The experimental dependence looks a bit more complicated, due to various imperfections and other effects that our model didn't account for, but the hysteresis curve is still apparent. Let's now look at how memristors can be applied for machine learning. The most simple neural network can be depicted in the following way. We have n inputs, x1, x2, x3, etc. Let's say we have a task of machine vision, which is to discern whether a picture shows a cat or a dog. So each input could be proportional to the intensity of a pixel in the camera matrix. Each input is then connected to a node, or an artificial neuron, the only property of which is the number called weight, denoted as W1, W2, etc. After passing through the nodes, the paths go to an adder, which calculates the sum of xj times wj for all j's from 1 to n. Then we say that if the sum is more than some threshold b, then we see a cat, and if it's less or equal to b, then it's a dog. The machine learning task is to find the values of the weights, which would yield highest fidelity for recognition. And here, memristors can actually play the role of artificial neurons, where the weights will be just their conductances. An example of a memristor-based neural network is a crossbar, where current passes from the green electrodes of the top layer down through an array of memristors to the yellow electrodes of the lower layer. And each of the lower electrodes here would act like an adder, since the resulting current through it equals to the sum over all voltages times the corresponding conductances. Memristors are actually self-learning, since the weights are adjusted by the flowing currents during operation, and the machine learning task comes down to finding the ranges of values of the thresholds for these electrode adders. Current memristors include a plethora of semiconducting films of metal oxide and organic compounds. There are several conditions a good memristor should satisfy. First is that the ratio of R off to R on should be greater than 10. That's because we need to distinguish well between the off and on states. Then high endurance. A memristor should endure no less than 10,000 cycles of switching between on and off states. Then, high stability. A memristor should be able to preserve its resistance state for an extensive period of time. For machine learning applications, it is important for a memristor to have high plasticity, which means no less than 16 different resistance states. The threshold energy for switching between on and off states should be lower than 10 picojoules. So far, a memristor that would satisfy all these requirements hasn't been found, but I believe it's a matter of time, as the field is rapidly developing. So far, we've only talked about classical memristors that show hysteretic behavior in the current voltage plane. And even though memristor technology hasn't reached feasibility yet, the researchers in the field took a step further in 2016, when a quantum memristor was theoretically proposed by Pfeiffer and colleagues. Why go quantum? Even though quantum technologies are very challenging to realize, quantum computations are actively developing as they provide speedups for certain problems. For example, Shor's algorithm for finding the prime factors of a large number is exponentially faster than the classical analog. Grover's algorithm for searching an unstructured database provides a quadratic speedup. The variational quantum eigensolver allows efficient approximation of Schrödinger equation solution, which is useful for quantum chemistry. These speedups are due to the ability to utilize quantum effects called superposition and entanglement. For example, superposition allows a system to effectively be in more than one state at the same time, which in terms of computation means that we can process several streams of data in parallel instead of one at a time. You've probably heard of a famous paradox about Schrödinger's cat. In a sealed box, there is a cat that has a 50% chance of decaying, a detector, and a vial of poisonous gas that gets broken by a mechanism if the detector registers the decay, killing the poor cat. Since the decay of a single atom is a random process, meaning that it might decay next second or in 1,000 years, it effectively exists in a superposition of two states, decayed and not decayed. Consequently, the cat has to also exist in a superposition of two states, dead and alive. When the concept of superposition in quantum theory was first proposed, Schrödinger came up with this thought experiment to demonstrate the alleged absurdity of the concept of superposition. Indeed, how the cat can be both dead and alive at the same time. In fact, quantum superposition is a very fragile thing, and it cannot persist in such large and not precisely controlled systems, like our box and its contents. Every particle interaction introduces a small random factor, which destroys superposition, making only one state possible. Quantum computers, on the other hand, are precisely controlled systems. They can use quantum superposition to operate with quantum bits, which are superpositions of ones and zeros instead of regular bits that are either 1 or 0. So a state of quantum bit, or a qubit, can be written as an arbitrary combination of 1 and 0. For example, alpha times ket 1 plus beta times ket 0, where the sum of alpha squared and beta squared has to be equal to 1. Quantum mechanics is a theory which describes smallest objects in the universe, like elementary particles, their properties, and interactions. Each measurement performed on an elementary particle is a form of physical interaction which affects the state of both the probe particle and the subject particle. Since it's an extremely delicate process, all physical properties are described in terms of averages and probability distributions. A fundamental object of quantum theory is called the wave function, which is a square root of a probability density of some property. An example of such property can be a spatial position of an electron in an atom. Electrons in atoms occupy specific orbitals, and each orbital has a certain probability distribution of where the electron could be found. For the lowest orbital, we have a spherical distribution, hence the electron can be found anywhere within that sphere. For higher orbitals, we have more complex shapes, as you can see in the pictures. To obtain these wave functions, one has to solve a Schrödinger equation, which reads that the result of a total energy operator, H, called Hamiltonian, acting on a wave function psi, has to be equal to total energy, E, times psi. For a free atom, the Hamiltonian consists of two terms. The first one is the kinetic energy of an electron, and the second one is the energy of electric interaction between the electron and the nucleus of the atom. Now back to quantum memristors. A quantum memristor based on quantum photonics was first proposed in 2018 by Sons and colleagues. It uses a tunable beam splitter, a device that reflects photons with a certain probability R. There is also a single photon source, and similarly to the decay of a radioactive atom, the process of emitting a photon is probabilistic. Hence, what's being emitted is a superposition of a single photon and a vacuum state. Psi equals to alpha ket 1 plus beta ket 0, where alpha squared and beta squared are probabilities of emitting and not emitting a photon respectively. Their sum equals to 1. If we send psi as an input onto the tunable beam splitter, the output state will have ket 1 multiplied by the factor 1 minus r, because 1 minus r is the probability of passing through the beam splitter. To obtain memristor behavior for this system, a feedback procedure has to be implemented. A detector measures reflected photons, and the measurement results are used to change reflectivity r. As it turns out, this scheme yields hysteresis if one plots the average number of photons for the input state versus the average number of photons for the output state, which confirms that this device possesses memory. Later, in 2022, an experimental chip based on the improved version of this tunable beam splitter scheme was realized by Spangolo and colleagues, making it the first experimental realization of a quantum memristor. The authors have also numerically demonstrated the quantum advantage. On a scheme of 3 quantum memristors arranged into a reservoir network, accuracy of image recognition was 24% higher with quantum input compared to the classical input. Their reservoir scheme uses only 1,600 tunable parameters, and it was able to reach accuracy of over 90%. Schemes based on classical memristors could achieve similar accuracy only with over 500,000 tunable parameters. The research group at our Optics and Complex Quantum Systems Laboratory focuses on constructing highly stable optical clocks and developing quantum processors using ultra-cold ions as the platform. In the pictures, you can see how these quantum processors actually look in an experimental setting. Ions allow to store quantum information using superposition of not just 2 states, like 1 and 0 in qubits, but 4 states, and this element is called qubit. In 2022, one of the world's first universal ion trap quantum processors was created by our group, possessing 16 qubits encoded in 8 ions. These developments require tackling complex engineering challenges to enable successful quantum operation with ions. An ion trap with optical access along 2 axes was designed. Additionally, an innovative scientific solution was proposed to utilize a quadruple optical transition at 435 nanometers for encoding information in ytterbium ions. And of course, the new research direction is quantum memristors. We use the platform of trapped ions, and in terms of theoretical principles, it is similar to the photonic quantum memristor we've discussed. For an ionic memristor, 3 levels in an atom are chosen: a ground level, an excited level, and an activation level. When laser pulses at a certain frequency 1 are shown, the population of electrons begins to oscillate between levels G and E, ground and excited states, as you can see in this plot with red and gray curves. Then another laser pulse at frequency 2 is used to bump some electrons from the excited level up to the activation level. A feedback procedure here is used as well. The population of the activation level is measured to adjust the parameters of the second laser. A hysteresis curve is obtained for this system when the average electron population of the excited level after the second pulse is plotted against the same population before the second pulse. In summary, we've discussed devices called memristors that could potentially revolutionize electronics due to their passive memory storage and energy-efficient operations. Memristors can be used as analogs of neural synapses in machine learning and neuromorphic computing applications. Moving forward, quantum computing provides a further boost to the memristor technology due to utilization of quantum superposition and entanglement. The latter research direction is actively developing at our laboratory, and we welcome any and all discussions and collaborations. Thank you for your attention, and good luck at the Olympiad.